Tomtex formatter uses the same 450 microliter pipetting design in a single tip pipetter. The formatter has an optional 4-place Sartorius balance. This automated weighing system has provided the opportunity to provide extensive data on pipetting methods and accuracy. Prior to the automated method, a manual method was used. The differences between the manual method and the automated method were as expected. Automation is very repetitive, allowing more samples to be recorded with a higher level of confidence. Black and white data is difficult to visualize for trends. This chart shows the actual gravimetric weighings at 27 different volumes for a total of 405 data points. The accuracy of 3% was chosen as the target. If the accuracy was within 2% at any reading, it is shown in blue. If within 3%, it is shown in green. If greater than 3% in accuracy, it is shown in red. Typically, with an air displacement pipetter, when used at volumes that are less than 10% of the tip volume, there is a loss in accuracy. This is due to two basic reasons. First, of course, is simply volume ratio. A 1 microliter error at 100 microliters is a 1% inaccuracy. The same 1 microliter error at 10 microliters is a 10% error. The second reason is the volume of dead air within the tip. At a minimum, the dead air is equivalent to the tip volume. This data clearly shows the falling off of accuracy below 40 microliters. This preceding data was derived from the single-tip pipetter on the formatter. This next chart shows gravimetric data obtained from Tomtex Quadras. The Quadra is a 96-well pipetter. This data is based on an average reading of all 96 tips as opposed to the individual tip values derived with the formatter. The color coding has been changed. Blue on this chart represents an inaccuracy of better than 0.5%, and red is better than 2%. The difference is that the average value is a reflection of the instrument's mechanics. They are very repetitive. The single tip data shows the tip-to-tip variations. This relates to how did each tip surface wet or not wet. Did the tip deliver cleanly? Were there small droplets on the tip surface? The conventional method of aspirating a 10 microliter aliquot is to aspirate from a source and then dispense to the destination. When aspirating from the source, notice the droplets clinging to the tip exterior. They obviously have a negative effect on accuracy. If you're looking for 5% accuracy at 10 microliters, that only allows a 500 nanoliter excess. On the dispense motion, the piston displacement is not effective in clearing the tips of the residual that is held by capillary action. Again, an obvious negative effect on accuracy. Pipetting methods can improve accuracy. For this example, the Quadra is using a slow tip withdrawal after aspirating the same 10 microliter aliquot. Notice how the liquid within the reservoir has wiped the tip's exterior surface, providing a more uniform aspirate function. When making the dispense motion, if it is made at the bottom of the well, the dispense liquid will surround the tip orifice. Again, a slow withdrawal will have a beneficial effect. However, piston displacement alone does not provide the ability to clear the tips of the residual that is retained by capillary action. The Quadra has a unique ability to blow a burst of low air pressure through the tip orifice. It is referred to as a timed dispense in the Quadra program. The timed dispense function is more conducive to clearing the tip residual. In summary, to improve pipetting performance, use a slow tip withdrawal when aspirating from a source. Use the timed dispense function to clear the residual within the tip. Another method of improving accuracy at small volumes is to use the target method. Assume you want to transfer 10 microliters. First, use a mix function to aspirate and dispense back 30 microliters to pre-wet the tip. Then aspirate 50 microliters and dispense back 40 microliters before lifting the tip from the source liquid. The first 30 microliters pre-wetted the tip interior. Aspirating 50 microliters provided a higher negative pressure to aspirate the incoming volume. Again, P1 V1 equals P2 V2. By dispensing back from 50 microliters to the target of 10 microliters, you are using positive pressure from the pipetter piston for this dispense motion. The next step is the dispense function itself. With the quadra, dispense back 7 microliters of the 10 microliters with piston displacement at the bottom of the well. This leaves a 3 microliter volume within the tip. Use the time dispense function to blow this 3 microliter aliquot clear of the tip orifice. At 1 to 2 psi of air pressure, the 30 microliter aliquot is blown out with sufficient kinetic energy to overcome surface tension forces at the orifice, both internal and external. This results in a cleaner delivery of the desired volume. As stated earlier, to calibrate a pipetter, the piston is moved a set distance of 16 steps per microliter, and the actual volume delivered is measured. The first motion of the piston moves, for example, 30 steps or so, but fluid does not enter the tip because there was insufficient negative pressure to overcome the resistance to flow at the orifice. The next set of steps aspirates the liquid. To make the dispense, the piston must reverse direction. There is a mechanical backlash created that causes a small loss of steps without piston motion. Next, the piston must move another 30 to 40 steps to change the pressure within the tip. It was a vacuum holding the liquid column and must now become a positive pressure to make the dispense. The actual volume this complete motion delivered was 95.82 microliters. This means that to aspirate and dispense 100 microliters, the piston must move 16.6979 steps per microliter and not the original 16 steps per microliter. This calibration point is accurate for this complete motion of aspirating and dispensing 100 microliters. This chart shows the variation when aspirating 450 microliters and then making multiple dispenses of 50 microliters. The first and last dispense were not included in the average. The first dispense is low as a result of backlash due to both mechanical and pressure on the change of direction from aspirate to dispense. The middle volumes are quite uniform but are not calibrated. If you're going to make multiple dispenses from one aspiration, the first dispense should be made back to the source. The last 1 or 2 dispenses should be discarded or also returned to the source. The question that frequently comes up is whether there is a loss of accuracy if the tips are reused. It of course depends on the fluid being used. Assuming the tips have not been damaged, we have not been able to measure any difference in reusing the tips with water as the medium. If anything, there is a slight improvement. Polypropylene is basically hydrophobic. After polypropylene tips have been used repeatedly, they become more hydrophilic. This is really observed when using ultrasonic tip washing. Virgin or dry polypropylene tips will show drops clinging to the tip exterior on the initial tip washing. After 1 or 2 washings, the liquid appears to sheet off the tip surface as opposed to clinging in drops. In all of the gravimetric testing, we have not been able to measure any difference in accuracy when reusing the tips. Again, the caveat is testing was with water and the tips were not damaged. Ultrasonic tip washing is available for Tomtec's Quadras. The first question is always, what is the carryover? In all of the carryover testing by Tomtec and others, there has been no detectable carryover. If there was carryover, it was below the detectable limits of the measuring instrument. One test was made at Waters with their micromass. A similar test was made at SciEx in Toronto. On both of these mass spectrometers, the results were the same. There was no carryover. Each user should verify their own results in their application. However, the success of others indicates the value of testing. The saving in disposable cost and faster cycle times are the reward. Ultrasonic creates cavitations on the tip surfaces. This provides a scouring action for cleaning. The aspirate is made at the bottom where fresh water enters. The dispense is made above the liquid surface, allowing it to overflow the weir. Notice the use of the slow withdrawal on the last motion. This allows the washed liquid to wipe the tip exterior of droplets. In summary, with this DVD, we've endeavored to pass on our experiences in pipetting. We have highlighted some salient points in the Quadra design and why they are effective. We are constantly looking at creative ways that we can be of benefit to the users of our products. If we can be of further assistance to you, please call us. We thank you for your time and interest in our products.